whenever you want.
Okay, so welcome back everyone to the next of our mini courses. So this time it's my pleasure to introduce Raimundo Heluani, who's going to talk to us about Cairo Homology.
Thank you. All right, so it's great to be speaking here about this. Jethro has put a fantastic program, and it's nice that we're going to get some quiet in the next couple of weeks. It's been hectic here. So I'll be speaking in the next three lectures about Cairo Homology, but I think I'll disappoint many people right now. I'm not going to mention run spaces. I'm not going to mention factorization algebras. I'm not going to mention anything Cairo algebras. I'm not going to do any geometry at all. Most people here work on vertex algebras, and this is going to be focused on vertex algebra computations. So if you're hoping to see some run spaces, Bellinson and Renfeld's book is great. Frankel and Svensby's book is fantastic. I'm just going to stick to vertex algebras and linear operations. But today I wanted to give, so today is going to be the only day that I'll mention some geometry. And I just want to give some intuition as to what are the problems and what would be the ingredients in defining a theory of Cairo homology. And then I'll just switch towards the end of the lecture to elliptic curves, and we'll deal with the degree 0 case of Cairo homology. So today, I'm only going to give some intuition, essentially from Lie algebra homology. So we want to give a working definition, something that is going to be closely related to Cairo homology, but it's not going to be exactly that. So this is going to be a hand-waving or working definition. Which is the best I can do without mentioning technical details in geometry. And then I will want to get to relations with, so today we're going to see use C2 quotient. Because mainly I'm going to be talking about the degree 0 case. In the following lectures, I'll try to connect with the lectures of Anne last week on arc spaces, and I'll see what the role of arc spaces has in degree 1 Cairo homology. And so today I'm going to be taking a limit which is called the classical limit. In the following lectures, I also want to take a limit which is going to be the nodal curve limit or the moduli space limit, and connect with Jou's algebra, the associative algebra, and not the C2 quotient, which is the Poisson algebra. All right, so let's start with the intuition part from Lie algebras. So if G is your favorite Lie algebra, then the Chevalier-Eilenberg complex that computes the Lie algebra homology with coefficients in its module M has as components the kth J product, wedge product of G. You tensor this, well, let me take K plus 1. You tensor this with the module M, and the differential goes to the K minus 1 wedge product of G. Oops, thank you. All right, so perhaps it's a little bit better. Well, I'll just keep it like this, and I'm going to write both terms for the differential. So if you give me a guy here, let's denote this A0 tensor. I'm going to use the simple tensor, but I probably use wedge probably here. I'm going to get K. I'm going to have M. And the differential has two summands. One uses the Lie algebra action of G on M. So that's the M module structure. We have A0, AK. I is missing here. And then you just act by AI on M. And there's another summand that uses the multiplication of your algebra. So this is -1. I reserve the rights of getting all of these signs wrong. So I guess here the sum is from I is equal to 0 to k, and here I is bigger or equal than 0, less than j, less or equal than k. And what you do, well, you just take ai and aj out, you multiply them, and leave the other ones as they were. So ak. So m is untouched here, and I and j are missing in this tensor product. So we have two summands. One uses the Lie algebra action on the module, and the other one uses the Lie algebra multiplication, and it doesn't touch the module. And several homological theories in algebra look the same way. So if you take Hochschild homology of an associative algebra with coefficients in a bimodule, you're going to see two sums, one where you use the bimodule structure, and the other sum, which is just the multiplication on your algebra. Okay, so it's cyclic homology, Harrison homology. Many homological theories have the same sort of feature. And we would like to mimic this in Vertex Algebra. And there are several theories in Vertex Algebras. There are several attempts to construct in such a thing, such a complex for Vertex Algebras. But I want to gather something. So remember what a Vertex Algebra is. So just to set up notation, V now is going to be a Vertex Algebra. For now, not any other structure, nor a Vertex Algebra. So a Vertex Algebra comes with a multiplication, but the multiplication is funny looking. It doesn't land on V itself. It lands on Laurent power series with coefficients in V. And it takes two vectors, and it sends it to, I'm going to denote it this way. I don't see any reasons to use y of az. So that's the multiplication on the Vertex Algebra. It has a unit, which I'll eventually use, and that unit satisfies that 1 of zb is actually just b as a constant series here. So you see the multiplication has this extra parameter, and we have to deal with it. And although there's several theories that you can actually write of complexes with coefficients in v, like this, I like this phrase. I think I've heard it first time from André Enriquez, which is the fact that I should think of a Vertex Algebra, at least with some properties, for example, being quasi-conformal, being conformal if you don't know what that is, as some sort of way of painting. If you give me a Riemann surface, then I can paint the Riemann surface with that Vertex Algebra. And the idea is that, and I'll say a little bit more about this. If you give me your favorite smooth Riemann surface over the complex numbers, so let's say x is going to be a smooth curve, so smooth algebraic curve over C, then I will think of the Vertex Algebra as something that lives on all of this curve, is spread over the curve. So V is spread over X. And I want to think of this multiplication as what happens when I make 2 points collide. So I'm going to have some sort of vibration. I'm going to have a vector bundle, an infinite dimensional vector bundle with a connection on the curve. The fibers are going to be identified with V. So if I pick a point here, and I have a vector in the fiber that I identify with A, and I pick another point, and I have my fiber going to be identified with V, and I have my vector B there. As these points collide, I want to see this multiplication here. So instead of using this formal variable z, it might be convenient to use a formal variable z here, formal variable w there, and as the points collide, I want to see the multiplication that would look like A tensor B going to, I was going to use y, A of z minus w, B, reflecting the fact that this expression here should be singular as z is equal to w, which is what happens for vertex algebras. But the nice thing of viewing vertex algebras this way, of something that is spread over the whole curve, is that I get to think of module in two different ways. I can think of a module also spread over the curve, or I can think of a module just supported at a point. So modules, so if M is a V module, and now I'll say a little bit more about how to spread over a curve of vertex algebra, but this requires some structure on the vertex algebra itself. It requires an action of at least some part of the Virasoro-Lie algebra to make this coordinate independent. But to talk about a module supported at a point, you don't need to have any structure on V. So when I say V module, I'm not even requiring to have T acting on V. If I wanted to spread it over the curve, I will need some extra structure on the module. But if I just want to have my module sitting on top of a point, I don't need any structure. So I'm going to pick one point, let's say X on my curve, and I'm going to have my module here. And again, I want to think of the multiplication. Remember, I will have my vertex algebra spread everywhere. I'm going to pick an M in my module, a vector A in the vertex algebra, and the module structure, which is for vertex algebras, is a map from V tensor M to M Laurent power series in one variable. Now this variable, I'm going to choose it to be Z minus X, just as it was here, Z minus W. For that multiplication, it's going to send A tensor M to A of Z minus X acting on N. And that's how I want to see my module multiplication and my vertex algebra multiplication. But the nice thing about that picture is that now I get to talk about modules, several modules supported at different points. And I can try to look at the homology of a vertex algebra with coefficients on a bunch of modules supported at different points in my curve. And that is the content of what Cairo homology is. So what we want to do is, mimicking what happens for Lie algebras, I would like to construct a complex whose data is the following. I want to start with X, again, a smooth curve over C. A bunch of points on that curve. So these are different close points on the curve. I want to start with a vertex algebra. But, well, this vertex algebra will need to be quasi-conformal. If you do not know what it is, just take it to be conformal. So it has a conformal vector. For all practical matters, this is what we want. And a bunch of modules, each one sitting on that point xi. And these modules, in principle, do not need to depend on anything. But the outcome of this data should be some complex that depends on all of that data. So the curve, your bunch of points, the vertex algebra, and the bunch of modules where you're taking coefficients. It's a homological complex. And the homology of this complex is going to be called homology. Will be the chiral homology of the curve X with coefficients in that chiral algebra with supports on the module M. So I don't want to spell that out, but the homology of this complex is called the chiral homology. And let's see what kind of what shape should that complex have. Okay, so if I want it to be the same way as for a Lie algebra, I should have a bunch of factors corresponding to the algebra itself, one factor corresponding to the module itself, and the differential should have two summands, one that uses the multiplication on the algebra and the other one that uses the module action. Okay? So the first attempt we will want to have is something along these lines. We will take our algebra, k plus 1 times, and we will take our module, well, let me just pick one module. It's sort of like useless to do this for many points. I'm going to do this in detail for many points in a second. Let's just take only just one module sitting at one point. And if I want my map to be like this, to k factors tensor my module, then I need to deal with the fact that I need to multiply them. And to multiply them, well, what can I do? I'm going to have two summands. So let's look at the first one. AK, tensor M. So one of the summands should be along the lines of, well, assign this whole vectors left alone, except I is missing. And then in the module, well, there's no other choice. I have to act with AI. What should I put here? Acting on M. But whatever I put there, it's going to land in some Lorentz series. It's not going to land in this space. And I have to deal with that. So let's decide that I'm going to have these k factors associated with k points in my curve, let's say z0 to zk. And this guy is on x, so I would want to put here something like zi minus x, so that it's singular when zi is equal to x. And something similar for the multiplication. So this is the term that we want to work out in detail in a second, this summand. But we have another summand that will have to deal with the multiplication. And that summand should look like this. So again, minus 1 to the I plus j plus 1. And again, I might get this sign wrong. And this is not the form that I'm going to have. We get to choose. Oops. Okay. I'm going to take AI. I think I'm using upper indices. AI. Now zi minus zj on aj, and leave all the other factors as they were. Here, I and j are missing. So this is more or less what I would want to have. But I see immediately that I have to deal with these formal parameters. So this differential is not landing on this space. So either I add the parameters zi to zk and the point x to both sides of the complex, or I make them disappear out of this differential. I can make disappear some of them. So that's a technique that actually works. Instead of looking at this whole formal power series, I can look at one coefficient of that power series. I could look, for example, at the residue of this thing. So I can integrate out one of these variables. I'm going to be left out with x there. The problem of integrating this out, one of these variables, is on this multiplication. So I could look at killing zi, but then I would still have zj. Of course, if I only look at this sort of power series, and I only look at the normally ordered product, that would be the coefficient of zi minus zj to the minus 1, all zi and zj disappear, but that's going to be a homological complex that would only read the normally ordered product on the vertex algebra and will not read any other structure. So I really want to see the OPE because that's what the vertex algebra uses. Well, the way to deal with that, we've seen this already before. In the Borges identity, we had an extra function or an extra monomial that we're allowed to test. So instead of like just taking residues of those expressions, I'm going to allow to multiply here by monomials or by functions on the zi's, such that when I take a residue, I can see all coefficients of this power series. And that's what we want to do. So the first thing is allow functions. We're going to correct this in a second. Functions on the zi's on both sides. The second one is make everything independent of the zi's. Make everything independent of the coordinates chosen. And then there's some other subtle things that we need to deal with, which are the action of the symmetric group. In the Lie algebra, I didn't take a tensor product, I had a wedge product. So the symmetric group on k plus 1 elements at here, the symmetric group on k element acts here, and I need to deal with that. So actions, appropriate axioms, actions of the symmetric groups. And there's an extra one that I hope to deal with that today, which is appropriate actions of vector fields. These vector bundles would come with a connection, so I would say actions deal with the action of vector fields on X. Well, if I wanted this to be a multiplication on the vertex algebra itself, I need a way of identifying one fiber of V with another fiber of V. And that's a connection on this fibration. So once if I have a connection, then I really want to look at flat sections and not just arbitrary sections. OK, so let's start to make this complex an actual complex. And let's try to make this complex at least a complex that computes what I would want to call H naught. And remember, in Lie algebra homology, to compute the 0th degree Lie algebra homology of G with coefficients in a module M, I don't need to use the bracket of the Lie algebra G. I only need to use the module structure. So if I want to compute Cairo homology in degree 0, I do not need the vertex algebra multiplication. I only need the module structure on my module. So this time, we'll take a curve. We'll take a bunch of points. This time, they will be many. So xi. And I'm going to put the module mi over the point xi. And I want to make a complex. And the first iteration would be this. This is not going to work, but it's going to give us an idea. So we're going to take one copy of the vertex algebra. And we're going to take all of our modules sitting at the different points. I would want to land on the modules, and I only need the module structure to construct this. And again, if you give me the algebra A is in the vertex algebra here. I'm going to take mi's in each one of the modules mi, and I will send it to a sum of. Well, this is going to be M1 tensor. In the ith position, I'm going to act with my vertex algebra operation. So this is going to be A of z minus xi. But now, let me just leave it like that. Oops. Acting on mi. And here I'm going to put mn, which is the last guy. Well, this doesn't land here. So I can take the coefficient of z minus xi to the minus 1. So this just means the coefficient of z minus xi to the minus 1. And this does land here. So this at least wants to look like a correct homology theory. The problem with this is, as I said before, this does not see anything but the minus 1 product. So in order to see the minus 1 product, let me allow functions here. So let me allow a function on the whole curve that is going to be allowed to have singularities at each one of these xi's. Oops, run out of space. Let's put this here. So this is a function on x minus these points xi's, and it's holomorphic away from those points. So if you give me such a function, let's choose coordinates close to each one of these xi's. So whenever you have such a function, you can expand this function close to each one of the points. So this is going to be a sum of f, well, let's say ik. The I just says around which point I'm expanding. And k is going to be bigger or equal than some integer number n. And, well, this is going to be a function of a formal variable, which is the formal coordinate that I'm going to use there. So zi minus xi times zi minus xi. Oops, sorry. These are the coefficients. I'm going to put zi minus xi to the k. So that's the expansion of that function near the point x. And I can do that. I can just multiply this by that function, by f. And now we can read explicitly what is this residue. This has the following form in terms of vertex algebra language. This is going to be the sum over I, and then the sum over k. This n, of course, might depend on I. Let's just take the minimal one. And now you're going to have fik, which is a constant. These guys are complex numbers. And here you're going to have m1 tensor. And in the ith component, you're going to have to put a, the kth product with mi. Mn. Well, this one is very close to being the right Cairo homology, namely the quotient of this thing modulo the image of this differential. I would want to call it the zeroth Cairo homology. And the problem with this is that this is coordinate dependent. This does depend on the coordinates that I've chosen around each point. So let's fix that. And this is, again, going to be the first approximation to fixing that. Instead of taking functions, and now I'm going to, yes? No, so here, when I take, so the only singularity that I have here is z minus xi. So when I take the -1 product, all of the formal variables disappear. And that's what I'm reading here, just this kth product, and this is just a constant number. This is the constant that appears as a Laurent coefficient of my function near that point. Well, yeah, and this k here coincides with that k there. All right. But again, the problem, the deeper problem here is that functions is the wrong choice. If I change my coordinates, then what happens is that this homology might depend on the coordinates that I've chosen for my curve. So in order to make that coordinate independent, and here I'm going to use something about vertex algebras, my vertex algebra is not going to be arbitrary. In that expression that I wrote there, the vertex algebra is arbitrary. So let's suppose that my vertex algebra is a conformal vertex algebra. I need slightly less. I need it to be quasi-conformal. And it's graded by z plus. So these are the components of conformal weight n. And let's suppose that the dimension of n, the dimension of Vn is finite for every n. So the slight modification I'm going to do there is going to be the following. Instead of taking arbitrary functions, I'm going to take vector fields. I'm going to take sections on x minus all of these points, xi's. And instead of taking the ring of holomorphic functions on the curve x, I'm going to take the canonical sheaf of x. So this is the dual annihilation sheaf of x. And I'm going to take to the minus n power. This is sum over n. So this is the tangent bundle tensor with itself to the end. And I'm going to take Vn here. And then the tensor product of all these mi's. And the differential would land on the tensor product of all these mi's. And this is the best approximation I'll give. So again, how does one do this? Well, it's exactly what I just wrote there. Locally, you pick a trivial. Once you fix your coordinate, the tangent bundle gets trivialized. Right? A coordinate, let's say t, leads to a trivialization of the tangent bundle d by dt. That's a vector field where this coordinate is well defined. So your section here that you may want to call this tau, you have your A. Well, if the tangent bundle gets trivialized by this, then this guy here gets trivialized by d divided by dt to the n. This vector A is a vector of conformal weight n. And we have our mi's. And we will send this to, well, exactly the same expression that I wrote there. So this is going to be a sum over I and k of tau I k tensor m1. And in the ith position, I'm going to put A, k, mi up to mn. Probably that's not visible, so let me write it again. Tau ik tensor m1. In the ith position, I'm going to put the kth product of A with mi, mn. Let's remove this. So that's going to be my differential. And this tau ik is the expansion of this section near the point I. Okay? So this tau is going to be written near that point I as the sum of tau ik times t, well, I've chosen t, minus xi to the k d by dt to the n. I can choose those expansions. Now, this is the right Cairo homology. And it fails to be the right definition by a little bit, which I will not explain, but I will tell you why this is the right, it computes the right homology at least. So I'm going to define the zeroth Cairo homology of x. I will define this zeroth Cairo homology of x, this bunch of points xi's, my vertex algebra V, and my bunch of mi's, to be the zeroth homology of that, to be the quotient of the tensor of all these mi's divided by the image of that differential. Now, for those of you who know about, say, for example, Frankel and Vensvy's book, what happens is that you don't really have, your vector bundle doesn't really look like a bunch of copies of the tangent bundle. So in reality, what you have is this. So in real life, to make this actually coordinate independent, to make this coordinate independent, what happens is that we're going to construct a vector bundle, a quasi-coherent sheaf on the curve x, with a connection on the curve x that is going to be a direct limit of vector bundles with a flat connection. So this is going to be a direct limit of bundles with a connection. This is actually filtered. You're going to have 0 inside of this 0. Well, let me write this as v less or equal than 0. So this is going to be built out of all the vectors in the vertex algebras that are of conformal weight less or equal than 0. And this is going to be included in another vector bundle of conformal weight less or equal than 1, in another vector bundle of conformal weight less or equal than 2, and so forth. And this guy here is going to be the union of all of those. But the outcome of that construction is that the associated, so that this bundle that we're constructing with a flat connection is a limit of subbundles with a flat connection, and, well, the connection is not compatible with this, so the connection goes to the next one. But the whole point is that the associated gradient to this bundle is going to be of that form. So we're going to have a short exact sequence of this form. Let me write it like this, into v less or equal than k. And the co-kernel here is going to be exactly what I wrote there. So the dualizing sheaf to the minus k tensor with our space of vectors of conformal weight K. So the complex written here, well, the right complex would be not use this, but use sections of this vector bundle with connections. So the right complex would look like this. You would look at x minus xi's, sections of this vector bundle, which is going to be built out of this many extensions, on the curve minus your points. You're going to take the tensor product of your modules, and you're going to land in the tensor product of your modules. But this complex is filtered, and it's filtered by this filtration. And the associated gradient to that complex, because of that statement that I made there, is this. So this actually computes the right homology in degree 0, as long as I have points where I have my m's, so that the curve minus a bunch of points becomes an affine curve. Okay, so this is as much as I'll say about Cairo homology in degree 0. This is going to be the right definition. This gives the right Cairo homology in degree 0 for a curve with a bunch of points and a module. And there's many things that you can say. So first of all, I can move now my curves and the points. So if xi's move in the moduli space of genus G curves with n points, then these complexes, the complex I defined, defines a bundle, gives a bundle, or a complex of bundles, with a projectively flat connection on this space. And I want to describe this precisely in the case of the Genus1 curves, projectively flat connections. On MG. Well, I'm technically lying here because if I want to move the point xi's, then I need to be able to identify the fibers. On xi, I was putting my module m, and I didn't require anything on my module m. So if I really want to move this point xi, I need to identify this fiber mi with another fiber with the same mi. So I cannot put arbitrary modules if I want to move the points. So if I want to move the points, my modules should be conformal. In the case that I'm going to be interested in, which is the case of elliptic curves, or the case of P1, where I have a global coordinate, I don't need full conformality. I just need to have T acting on the module M, which is a requirement that people in Vertex Algebra sometimes put. But the point is that if I want to move the points, then it's reasonable to expect that the modules are not just arbitrary modules over a Vertex Algebra. So this fact that this gives rise to bundles with flat connections, this is due to Beilinson and Drinfeld. The whole theory is due to Beilinson and Drinfeld, so we should give reference here, Beilinson and Drinfeld. Although for this particular case of degree 0, the book of Frenkel and Benzvi is fantastic. Beilinson, Drinfeld. See also Frenkel and Benzvi's. Now, recently, well, what we know is the following, and I'll give a proof of that in a second, at least for Genus1. Yeah, I think so. Is that if the vertex algebra V is rational and C2 cofinite, then the zeroth homology, well, H Cairo 0, these are called coinvariants, x, xi, v, and my modules mi. These mi's are now going to be positive energy representations. These guys are finite dimensional. And this is finite dimensional for any curve and any bunch of points in that curve. Interestingly enough, C2 cofiniteness appears as a condition here. which I still do not know really how to relax that. Rationality also appears. You do not really need rationality for this statement. Just C2 cofinite is good enough for arbitrary curves as long as you're in the smooth locus. But I'm going to reference recent papers by Gibney, Tamiolini, Gibney and Tarasca. Although several names should be attached here too, I would say, I guess, what, the alphabetical order is going to be wrong, but Tsuchiya, I'm not sure if I'm spelling it correctly, Bueno, Yamada. In the case of affine algebras, then Tsuchiya alone claimed this for rational vertex algebras, and then there's also Beilinson. And Maser, I think, in the case of the affine, in the case of the Virasoro algebra. But the point is that what this, Maser, that's correct. It's not Beilinson. Thank you. I'm sorry? Yeah, so let me just, but the order is correct. Beilinson, Fagin, Maser. But the point is that these bundles extend to the boundary of the moduli spaces. So these bundles, so vector bundles with a connection on M, G, N bar, and the connection has regular singularities in the boundaries. In the boundary. So one nice thing about this result that would be very nice to have for higher Cairo homology is that it tells you, for example, it satisfies the following. It satisfies a factorization condition. So these bundles satisfy a factorization condition. And it's not clear to me how much of the rationality and the C2 cofinite condition is actually needed in their proof, but their proof actually uses both rationality and C2 cofiniteness. And the idea here is that you have your curve, you go to the boundary of the moduli space, and this curve becomes singular in the boundary. So here you have your marked points where you're going to put your modules, and in the boundary, this point is outside the singular one. So we're computing Cairo homology of our vertex algebra with coefficients in a module located at this point. And what you do is you take a resolution of this singularity. So now this guy is the normalization of that curve. These are the preimages of the node. And here is our marked point that has the module sitting on it. And the factorization is that the Cairo homology on this nodal curve, which I haven't defined. I've only used this for smooth curves. But what Damilini, Gibney, and Tarasca do is they define explicitly what Cairo homology is in degree 0 at least for singular curves. And then they claim, well, they prove that the Cairo homology in this situation, so this is going to be some H0 that has a module M sitting at the point P, is a direct sum of Cairo homologies in this normalization where you choose Mi. Let me tell you in a second what this is. Mi. This is going to be sitting at Q. This is going to be sitting at Q bar. And we're going to have still our module M in P. This sum is over I. And the idea is you're going to put a module Mi on this point Q, the contragradient module or the dual module Mi on this other image of the node Q bar. and you sum over all simple modules. So by doing this way, we've managed to compute the Cairo homology of this curve, and therefore of this curve, because these were bundles with connections, and this guy has some genus, and this curve has lower genus. So you can, by knowing the Cairo homology of lower genera curves, you can compute the Cairo homology of higher genera curves, at least in degree 0, due to this theorem. So we can, by going to the successive boundaries on the moduli spaces, we can compute all Cairo homologies in degree 0s by knowing them on genus 1. Okay? So that's where my focus is going to be. I'm going to move now to genus 1 curves. Before, yeah, so let me do that for genus 1 curves. Well, yeah, you can go to genus 0 as well. So if you, the thing is with, yeah, I want to consider genus 1 because I want to do, there's something special that happens at genus 1 with a point, with marked points, but it's true. So from genus 1, you can go to genus 0 by just writing your elliptic curve as a quotient of P1. Yeah, so what I would want to start avoiding from now on is the module insertions, and I'm only going to be talking about vacuum insertions, but then for that, I need to state another theorem of Ellinson and Renfrew, which I think we are going to prove at least in genus 1, is the following, is that the chiral homology, say you have your curve x, say you have a bunch of points xi, and we're going to add an extra point. Let me add the point y, which is different than all the previous ones. And you have your vertex algebra, and you have your modules mi's that live on each one of these points xi, but on the extra point that I added, I'm going to put the vacuum module, v. So v is on the point y. And then the statement is that this is canonically isomorphic to the chiral homology of x, xi, v, mi. So as long as you have a marked point, you can start adding as many times you want the vacuum vector. So this was proven by Zhu in the genus. So this is explicitly proven by Zhu in the genus 1 case. Zhu defines the duals of these vector spaces. He calls them conformal blocks, and he proves that you can find an n+1 point function in terms of an n-point function. So this proved this for you in the genus 1 case, where all these mi's are v. And this is proven in general by Bellinson and Drinfeld in a geometric way. This is called propagation of vacua in physics. Okay. So I want to do something concrete, so I'm going to move to genus 1 curves. Because there, we can study explicitly what's going on. And most of what I want to say, which is the connections with Zhu's C2 algebras and with Zhu's algebras and taking limits, will happen at that level, which is the level of elliptic curves. So from now on, let's take x to be an elliptic curve. So this is going to be the quotient of c divided by z plus z tau, which is isomorphic to the quotient of c star divided by z q. Here, tau is an element of the upper half plane, and q is e to the 2 pi I tau. So the map, this isomorphism of x with itself, this isomorphism is given by the exponential map. So this curve is going to come with one marked point x, which is the image of 0 in this picture, or the image of 1 in this picture. And in that point, I'm going to put the vacuum module. Okay. So I'm interested in understanding this, our complex. Our complex now is very simple, because since omega x is trivial, I don't need to care about taking sums of powers of omega x inverse. Right? So they're all trivial bundles. And since I have this, then my complex looks very simple. This looks like functions, honest functions, on x minus the point x, OX, tensor V, tensor. I'm going to put one module at 0. This module is going to be V soon, but I just wanted to keep it separate for a second. This goes to M. And the map here now is, again, you have a function f of the coordinate t. This coordinate t is the given coordinate on C. It's singular at t is equal to 0. T, A, and a vector m. And you send this to the residue at t of f of t, A of t, m. That's the differential. So what I want to prove is that this actually gives you a vector bundle with a flat connection on the moduli space of elliptic curves as I move the parameter tau in this space. Okay? And I want to prove that this thing is finite dimensional on conditions on the vertex algebra V. But it's a very explicit complex, and it exactly agrees with my geometric one because I have this isomorphism here, so I don't need to be careful about sums. You also realize that for this to be well defined, I don't need to have V to be a conformal vertex algebra. The only thing that I need is a translation invariance that I have on any vertex algebra. Okay? So any vertex algebra gives me bundles with flat connections on elliptic curves and in affine lines. Okay. Okay, so I want to compute this, this homology. And for this, we're going to use that we understand very well what is this space. So this space of functions on an elliptic curve minus a point, well, this actually is a C-linear span of some particular functions. I can have a constant function, it doesn't have any singular point, or I can have the Weierstrass P function, or I can have the derivative of the Weierstrass P function, and so on. So let me tell you what these functions are. Actually, for all I'm going to do, I don't really need any expression for these functions. I only need the fact that this is a section of O, this is a section of O twisted 2 times by the marked point x. So I need that this is a section here. This is a section of this twisted like this. This is a section of O3, and so forth. That's the only thing that we will actually need. And this is important because, in principle, we should be able to replace all these funny-looking expressions that I'm going to write by abstract sections of those bundles and never use these power series expressions that I will use in the next few boards. But just for the sake of completeness, and since this is a school, let me define what P is. This is going to be a function, a holomorphic function, metamorphic function on all of C that is going to be invariant by the translations by this lattice. So this is going to depend on T and tau, and it's going to be 1 divided by T squared plus the sum over M and N. This is in Z2, just that I'm going to require that these two things are not 0 at the same time. So that's this line here. I'm summing over everything that will not make this summand singular. And it's going to be 1 over T minus M minus N tau square minus 1 over M plus N tau square. So this series converges. And you see it on the nose that it has poles at P has a pole of order 2 and no residue at M plus N tau. T is equal to M plus N tau. And it has no other poles. And this guy is bi-invariant, namely T plus M plus N tau is equal to M of T tau. So this is a well-defined function. So this P is a well-defined function on the curve x minus the point x. It's holomorphic everywhere. So it goes down to this quotient by Z2. So that's a well-defined function here. Now, by the Riemann-Roch theorem, you know exactly what's this dimension of the space of holomorphic functions with a prescribed pole, but probably you need much less than the Riemann-Roch theorem. But we know what are the spaces of the dimensions of the spaces of holomorphic functions with prescribed order of poles on these curves. And it turns out that then they all have to be of this form. So any function on an elliptic curve, on a smooth elliptic curve, is a linear combination of these functions. So the constant function 1, this function p, and all of their derivatives. Okay, so this gives us an explicit description by integration by parts of what the zeroth chiral homology is. I need to do something with this noise. Okay. So you see, I have this quotient by all functions. But the quotient is given by an integral. This is a residue. So by recognizing that the residue at t of f of t, well, let me write it in a different way, of d by dt of anything is equal to 0, then I can trade derivatives on the function f by t, the translation operator on the vertex element A. So it's enough to kill 1 and the Weierstrass P function. So what we've proven is that the chiral homology in degree 0 of, well, the curve x, the point x, the vertex algebra V, and the module M, this is the quotient of M divided by A0 M, which is the differential of the constant function 1 and the residue at t of the Weierstrass P function of t, A of t acting on M. Yes? Oh, the residue of a derivative is 0. So the residue of a power series, let me write g of t, is equal to g minus 1, where g is in c of t. G is equal to the sum of g k t to the k. So the residue is the coefficient of t to the minus 1. So if I take the derivative of a function, since it's a Lorentz series, the derivative will never have t to the minus 1, because the logarithm is not, well, it's not allowed. So if I take the residue of a derivative, that's 0. So I can take the derivative in this expression with respect to t. And I know that the residue of d by dt in this expression is 0. But d by dt, let me write it here, d by dt of f of t times a t m is equal to f prime of t atm plus f of t t of a tm. And that's actually going to be the connection in my bundle. But I see how d by dt gets killed, so I can trade derivative on f by t acting on a. So I can trade, if I want to look at the differential of p prime or p second prime, by derivatives on a. So it's enough to kill these two guys, and I'm done. So now, let me give you a different expression for this. So I've given you an expansion of p of t on the whole of C, so that's a well-defined series. But what I need to compute this, remember, my rule was very simple. I needed a Lorentz series expansion of this function near the singular point. So for that, I need that series, and this is the series. It's P of t. And remember, this depends on tau. This is 1 over t squared plus, I'm sure I'm going to get this wrong, I wrote notes, so let me do this by trial and error. I think this is going to be correct. 2k plus 2 tau. Yeah, that's fine. And then I'm going to have a t to the 2k, and I think that's correct. So here, so that's the expansion of p near this point t is equal to 0. Here, these constants that only depend on tau are the Einstein series. So gk of tau, where it's defined, is the sum, again, mn, not both zeros at the same time, of m plus n tau raised to the k. This is nicely convergent whenever k is bigger or equal than 4, and this is my starting point in this series. All right, so that's the expansion. So what I see is that the Cairo homology is the quotient of m divided by the 0th product of the vertex algebra on the module and the -2 product. So this is the residue of t to the -2, and then I have all this tail. And this tail is completely irrelevant for now, but let me write it. So this is 2k plus 1, the constant g2k plus 2, and then a to the 2k on m. So you see, in Cairo homology, only the even modes of the vertex algebra appear. Okay, and I'm sorry, k bigger or equal than 1. So that's a very explicit vector space, which is the Cairo homology of a module, of an elliptic curve with coefficients on that module sitting at the mark point of the elliptic curve. Yeah. That's a very good question. Yes. So, yes. So this is a very good question, which the way I'm phrasing this thing here, this is just a polynomial because as k grows, a is a field and this kills m. Okay? But when you want to deal with all of the parameter taus at all time, so here I'm considering this as a constant because I fixed my curve x. But at some point I would want to move this parameter tau. So I need to understand what is this. And I would want this to have some sort of convergence in tau, which again is immediate. Okay, so that's it. And I want to claim that this is finite dimensional for some finite condition on the vertex algebra V. So let's do this for the case m is equal to V. Okay? So now I'm going to talk about filtrations. And this filtration that is going to appear today is going to be different than the filtration that we've seen so far. I'm not sure if we've talked about the increasing filtration. So I will need this statement, filtration on V. Actually, yeah, well, it doesn't matter. Before I move into proving, let me state a theorem of Jou. So theorem. When m is equal to V, so this is for the vacuum module, and V is C2 cofinite, and rational, you look at mi's. So again, I'm going to be computing the Cairo homology with coefficients in the vacuum module V. These mi's, which are going to be simple modules of V, are completely auxiliary. This is the finite set of isomorphism classes of irreducible modules. You look at the top space. So let me put mi on top. Mi top, which I think was also called mi bottom. So this is the lowest energy space of each one of these modules. And there exists an element ai on the vertex algebra V such that the zero mode of this ai is equal to the identity on mi top, and is equal to 0 on mj top when j is different than I. So we can find a bunch of elements on the vertex algebras that act as the identity on the top component of your module or as 0 in the top component of your other modules. Let me give you an example of that. And I'm happy that I don't have any of my physicist colleagues here because I'm going to give the first non-trivial example, but it's still going to be quite trivial. Let's take V1. I want to compute these things. V1 of SL2. So that's affine SL2 at level 1. this thing has two irreducible modules. It has the vertex algebra itself, and it has another module. So this has a top component of dimension 1, which has conformal weight 0. And it has another module whose top component is conformal weight 1/2. And, well, the vacuum element, the zero mode of the vacuum element acts as 1 on both sides. It acts as the identity everywhere. And the zero mode of the Virasoro element, the conformal vector, acts as 0 here and 1/2 here. So I can immediately get those two by looking at this minus twice omega, or looking at twice omega. So twice omega acts as 0 here, and it acts as 1 here, in the top component here, and this combination acts as 1 here and 0 here. So that's the basis. So the theorem of Zhu is that, well, let me finish the statement of the theorem. These AIs form a basis of Cairo homology. Of Cairo homology of X with coefficients in the vacuum module. X, the mark point X. So this is Cairo homology in degree 0. The vertex algebra V, and the vacuum module V put at the point X. Now, it follows from a theorem of, so this is not really the statement how Zhu proved it. In fact, I'm using Zhu's theory there, but this is much simpler to understand. I don't need to have convergence of characters. I'm not talking about convergence of anything here. I'm just giving you a couple of vectors in the vertex algebra, and I'm claiming they exist. And the problem is to prove the existence and to prove that these are bases, I'm using Zhu's theory. I would like to get this out of abstract nonsense. And let me tell you how that should come. So I'm going to state the theorem that comes now from Miyamoto. I'm going to attribute this one to Zhu, and this one is due to Miyamoto. I'm not going to spell this out completely, it's just the name of time, but replace irreducible by projective and M top by an appropriate level. By an appropriate level that might not be the top component of your module, and you still get a basis, and a basis for Cairo homology in degree 0. So now exercise, do this for the triplet algebra. I'm not sure if Azad is around. But out of abstract nonsense, these things are given as traces, which I won't have time to do now. Again, the point I want to make is that these statements I'm making here that follow from Zhu theories that we've already seen in the language of conformal blocks do not need any convergence of characters. And I've given you the basis of Cairo homology for V1 SL2 at, given these two guys. Let's prove that that actually is Cairo homology of V1 FSL2. And for this, I'll use filtrations. So filtrations on vertex algebras. So let me prove that statement, at least give one proper proof. So instead of looking at a decrease in filtration, this is going to be an increase in filtration, where I'm going to denote G minus 1 of V and everything that is negative to V0. This is going to be included in G0 of V, which is going to be the vacuum. And this is going to be in G1 of V, and like this. The limit of all this GP of V is going to be all of V. The intersection is 0. And what is this guy going to be? Well, GP of V is going to be the linear span of T to the N1, A, I1, T to the Nk, A, Ik. So you take K elements of your vertex algebra, you take derivatives of these guys, arbitrary derivatives of these guys, take the normally ordered product. So when I write a product on a vertex algebra, it's the normally ordered product. This is non-associated, just pile them anywhere. take this and require that the sum of the conformal weights of the elements that you used is less or equal than P. So these AIs are taken from a pool of generators. So AIs, J's, are generators of your vertex algebra V. And since a posteriori this does not depend on the chosen generators, you can take every vector of V that is homogeneous of a given conformal weight, because I need that is non-zero. Okay? So that gives an increase in filtration. And the theorem of Tomoyuki, that several theorems of that paper were stated, is that the associated grade, but not, I think not this one, the associated graded of V with respect to this filtration is isomorphic as Poisson vertex algebra to the associated graded of V with respect to the Lie filtration, the decrease in filtration. Okay? So that's a theorem that I will write in a following lecture because I'll need it, but not now. So that's an increase in filtration of the vertex algebra. Let me give you an increase in filtration of the space of functions on the elliptic curve. And the resulting filtration is going to be called the Hodge filtration. So the Hodge filtration so this is going to be a filtration on the space of functions on the elliptic curve minus a point, which are holomorphic. So I'm going to take G minus 2 of gamma. From now on, let me call this gamma 1. G minus 2 of gamma 1 is going to be 0. This is going to be included in G minus 1 of gamma 1, which is going to be the span of the constant functions. So these are going to be just the regular functions. And this is going to be included in G minus 2, in G minus 0 of gamma 1, which is all of gamma 1. So that's an increase in filtration that has 2 steps. Okay? So I get a filtration GP on gamma 1 tensor V. And again, I want to compute my Cairo homology with respect to, with coefficients in the module M, which is the vacuum module. Oops. This is filtered, this is filtered, this is filtered. Just take the tensor product of the filtrations. So this is the direct sum of Q, R, and S of GQ gamma 1 tensor G, R, V tensor G, S, V. And lemma, the complex is filtered. This filtration is compatible with the filtration. What is the complex we've written so far? So far, our complex looks like gamma 1 tensor V, mapping to V. I have the GP filtration in this tensor product. I have the GP filtration here. This complex is filtered. The differential of GP of this tensor product is inside of GP of V. Oh, thank you. Thank you. Less or equal than P also works. So let's explicitly look at that. I shouldn't have removed the series for the P versus P function, but let's explicitly look at that. I only care, well, you see, the associated gradient of my space of functions with respect to this filtration is very simple, because I get GR minus 1. Right, so the associated gradient is whatever half divided by the smaller space. So GR minus 1 of gamma 1 is just regular functions. Global sections of OX. Which is just one-dimensional, and it has this basis. And the associated gradient in degree minus 2, up in degree 0, of gamma 1, well, this is a free module. This is the free d by dt module generated by P. Modulo constants, that's what it is. I'm dividing constants, and everything is a derivative of P. So I have these two generators, and these are the two associated graded. Now, well, I need to analyze the differential of two things, either one tensor A, tensor B, and I want this to be in GP. So I'm going to take A, well, let me write it here. I'm going to take A in VQ and B in VP minus Q. Well, this is in degree P, is in the filter part in degree P, but the constant one is in degree minus 1. So let's add a 1. Now this whole thing, the tensor product, that guy is in GP. And this goes to A0B. And the other one is the Weierstrass P function, tensor A, tensor B. And this goes, well, now I'm going to need A in VQ and B in VP minus Q. Because this Weierstrass P function is in degree 0. So that tensor product is in degree GP. So both of these guys are in GP of the tensor product. So the differential of this, remember what it was? It was A minus 2B plus a sum of k bigger or equal than 1 of 2k plus 1, G 2k plus 2. These are constants, A 2k of B. So that's the differential of that element. And now I'll use the basic property of that filtration. That filtration is actually a filtration of vertex algebra. It's a good filtration if my vertex algebra is conformal. It's an abelian filtration. The quotient is a Poisson vertex algebra. And it has the property that if A is in GP and B is in GQ, then A and B is in, well, GP plus Q if n is negative, and is in GP plus Q minus 1 if n is non-negative. So it decreases filtration. That's why the OPE, you get to kill the OPE in the associated graded, and you get to take it as a Poisson lambda bracket. So that's the property of that increasing filtration. There's not entirely trivial to prove. Again, this is due to Lie. This is Heischen-Leig's paper. Okay? So what else I want to say? So perhaps one extra thing to notice about this filtration is that T of GPV is inside GPV. So the derivation is of degree 0 with respect to this filtration, which wasn't the case for this decreasing filtration. The decreasing Lie filtration has T of degree plus 1. The same thing happened for the Hodge filtration for functions. D by dt preserves this filtration, and is of degree 0. If I take the Weierstrass P function, the derivative is still in degree 0, and the constant function gets killed. So I have this compatibility with T being of degree 0 with respect to this filtration. Okay, but now I see something. With respect to this associated graded, this thing here is in GP, which was a claim because this thing should preserve the filtration. But this thing here is in GP. But all of this thing here is in GP minus 1. So all of this thing here gets killed in the associated graded. So the homology of the associated graded, we have a filtered complex. We take the associated graded, and that's a complex. So if I look at the associated graded with respect to this filtration G of the complex computing Cairo homology in degree 0, this thing here has in degree 0 homology is the quotient of V divided by V or A 0B and A minus 2B. And if you noticed, this is the quotient of RV, which is the quotient of V divided by V minus 2, by minus 2 product, divided by the 0th product, which is the Poisson bracket on RV. So as a corollary, whenever the associated scheme of a vertex algebra has this space being finite dimensional, Cairo homology, the space of conformal blocks, the space of covariance is finite dimensional. This is a trivial application of this thing. I mean, this is something that certainly is known to everyone here, but this is a very simple application, and I'm going to use the same technique later. So let me just spell out the corollary. So corollary, if V is any vertex algebra such that, well, I need the Lie filtration to be well defined. So let's take a conformal vertex algebra. If V is such that the dimension of RV divided by Poisson brackets on RV is finite, then the chiral homology, the dimension of H chiral 0 of the elliptic curve, D marked point, V, and coefficients in the vacuum module is finite, because it's less than this dimension. It's less or equal than this dimension. Okay, so the associated gradient is the 0th page of the spectral sequence associated to that filtration in the complex. So I have 5 minutes. Let's compute this, therefore, for SL2 at level 1. Okay? So, of course, we've seen, I feel a little bit ashamed that I've chosen this example, given that Anne spent lectures and lectures describing the structure of nilpotent orbits, but this can certainly be applied explicitly for all these affine algebras that we've been seeing in the last weeks. But let's just take, at a very naive level, SL2 at level 1. So this is the free algebra with one singular vector, and that singular vector is E minus 1 applied to the vacuum. So what is RV? RV is a very simple guy. So the RV of the universal one, we've seen that this is polynomials in the 3 generators of SL2, E, H, and F, with the standard Poisson bracket. So this is the symmetric algebra on G on SL2, finite dimensional SL2. And I need to divide by the Poisson bracket generated by E square. So, Poisson ideal generated by E square. So let me define that. This means the Poisson ideal generated by E square. Let's compute that ideal. That ideal has E square. Now, the Poisson bracket of F with E square is 2H E, perhaps minus 2HE, but it doesn't matter. HE is therefore in the ideal. The Poisson bracket of F with this thing would give me some FE plus H squared. But here, there should be some coefficient. So I think this is FE plus H squared. The Poisson bracket of F with this thing is going to give me that H is in the ideal. And the Poisson bracket of F with this again is going to give me that F squared is in the ideal. So this generates an ideal as a commutative algebra on this guy, and the quotient is RV. Okay? So RV is the quotient of this polynomial algebra divided by this ideal here. And now I want to compute RV modulo Poisson brackets. Well, so RV, what is RV? As a vector space, I have the constant functions. I have the 3 linear guys that didn't get killed in this ideal. So I have E, H, and F. And out of the quadratic ones, I realize that H multiplied by anything is 0, F squared is E squared is 0, and F squared is 0. So whenever I see an H squared, I can trade it by EF. So I can take this as a basis. And anything that is cubic is already 0 in that algebra. Okay? So this is a basis for RV, which is of a dimension 5. So this is a basis of RV, C-span of this. And now I want to quotient by Poisson brackets. But SL2 is a perfect Lie algebra. So everything here is a Poisson bracket of something. So RV divided by Poisson brackets of RV is of dimension 2. The dimension of this guy is 2. The basis, I found one explicit basis, the constant element and the Casimir element. And these were the basis for, this actually corresponds to the vacuum vector on the vertex algebra and the conformal vector on the vertex algebra. We know that the Cairo homology has dimension less or equal than 2 by that theorem. And I've given you two vectors that is easily seen that they are linearly independent in Cairo homology. So we've proven that the space of the Cairo homology of SL2 is of dimension 2 is given by a basis of naturally defined vectors acting on the simple modules of level 1 SL2, and we've never used convergence of characters, which is the hard part of Jou's theorem. Never used this. Okay, I'll stop here, and I'll continue on Wednesday. Oh, well, you see, you would never have equality in interesting algebras, right? So typically what happens is that, let's say E8, for example, level 1, that will have, actually, no, I take that back. So I do not know how to, I don't have any control over this Poisson homology. I don't really know. So I'd expect that this thing is really a bound. So for E8 at level 1, you know that you have Cairo homologies dimension 1. The Poisson algebra, RV, is of dimension 240, something like this. But I do not know it as a Poisson. I do not know what the Poisson homology of that algebra is. So I wanted to give you that one already as a counterexample. But I do not know what the Poisson homology of that algebra is. So I will have to actually think about this. But let me get back to that question on Wednesday.